It's generally not permissible to splice conductors from different circuits unless it's a multi-wire branch circuit, or MWBC. An MWBC is a single circuit that has multiple hot conductors sharing a common neutral conductor. If you want to bring in a 14/2 Romex from another circuit to feed a light, this is only allowed in a few scenarios. 1. The existing circuit is MWBC. The new Romex can be connected to the hot and neutral conductors of one of the MWBC circuits, provided that the amperage rating of the circuit breaker is not exceeded. 2. The existing circuit is not a MWBC but shares the same neutral. If the existing circuit shares the same neutral with another circuit, you can connect the new Romex to the hot conductor of the existing circuit and the shared neutral. However, you must use a handle tie to secure the neutral conductors together. 3. The existing circuit is not a MWBC and does not share the same neutral. You cannot connect the new Romex to the existing circuit. You must run a separate circuit for the light. If the existing circuit is not MWBC and does not share the same neutral, you do not need to ensure that the hot conductors are on separate phases. The 2002 National Electrical Code, NEC, allows for the use of handle ties to connect neutral conductors from different circuits when the circuits share the same neutral. It also prohibits the splicing of conductors from different circuits unless it is MWBC. Based on your description, it is not clear whether the existing circuit is a MWBC or shares the same neutral. If it is not MWBC and does not share the same neutral, you cannot connect the new Romex to the existing circuit. If it is a MWBC or shares the same neutral, you can connect the new Romex as long as you follow the proper NEC requirements, including using a handle tie if necessary. When dealing with electrical wiring and circuit modifications, always consult the latest edition of the National Electrical Code and local electrical codes to ensure compliance and safety. Here are some key considerations and expanded explanations regarding splicing Romex cables from different circuits. Firstly, understanding multi-wire branch circuits is crucial. A multi-wire branch circuit, or MWBC, consists of two or more grounded conductors that have a voltage between them, and a neutral conductor that is common to all conductors. MWBCs are typically found in residential and commercial settings to maximize circuit capacity using shared neutral conductors. Secondly, identifying shared neutrals is important. If the existing circuit you're considering tapping into shares a neutral with another circuit, it means that the neutral conductor serves both circuits. This setup is common in older installations but requires careful consideration to ensure compliance with modern electrical codes. Thirdly, handle ties or common trip breakers are essential. When circuits share a neutral conductor, the NEC typically requires the use of handle ties or common trip breakers to ensure that all associated hot conductors are disconnected simultaneously. This prevents overloads and potential hazards. Fourthly, avoid splicing if circuits are independent. If the existing circuit is not a MWBC and does not share a neutral with any other circuit, you should not splice into it to power your new light. Instead, you must run a dedicated circuit from the electrical panel to supply the new light. Fifthly, amperage ratings matter. When connecting a new load to an existing circuit, it's crucial to verify that the circuit's amperage rating is not exceeded. Check the circuit breaker's rating and calculate the total load on the circuit, including the new light, to ensure it remains within the breaker's capacity. Sixthly, phase considerations apply if applicable. In three-phase electrical systems, it's important to balance the load across the phases to prevent voltage imbalances and equipment malfunctions. When adding a new circuit, ensure that the hot conductor is connected to a different phase than the existing circuit to evenly distribute the load. Seventhly, the 2002 NEC requirements are the baseline. The 2002 NEC allows for the use of handle ties to connect neutral conductors from different circuits when the circuits share the same neutral. It also prohibits the splicing of conductors from different circuits unless it is a MWBC. Eighthly, safety is the top priority. Before working on any electrical circuit, always turn off the power at the breaker and verify that the circuit is de-energized using a voltage tester. Follow safe electrical practices and wear appropriate personal protective equipment (PPE) to prevent electrical shock or injury. Ninthly, consult a qualified electrician. If you're unsure about any aspect of electrical wiring or circuit modifications, it's always best to consult a qualified electrician. They can assess the existing wiring, provide guidance on code-compliant solutions, and perform the work safely and correctly. 10thly, consider local codes and regulations. In addition to the NEC, local electrical codes and regulations may have specific requirements for electrical installations. Be sure to check with your local building department or electrical inspector to ensure compliance with all applicable codes. When splicing Romex cables from different circuits, always prioritize safety, compliance with the electrical codes, and proper wiring techniques to ensure a reliable and safe electrical system. Following points elaborate further on various aspects of electrical wiring and splicing, providing a more detailed understanding. Firstly, grounding and bonding considerations. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, trapping the circuit breaker and preventing electrical shock. Bonding ensures that all metal parts of the electrical system are at the same electrical potential, reducing the risk of shock. Secondly, wire sizing and ampacity. The size of the wire used for electrical circuits must be appropriate for the amount of current it will carry. The ampacity of a wire is the maximum amount of current it can safely carry without overheating. NEC Table 310.15 details the ampacities for different wire types and sizes. Thirdly, conduit and cable types. Electrical wiring can be installed in various types of conduit or cable depending on the application. Conduit provides physical protection for wires and cables, while cable assemblies, such as Romex, are commonly used for residential wiring. Fourthly, box fill calculations. Electrical boxes must be sized appropriately to accommodate the number of wires, devices, and fittings contained within them. NEC Section 314.16 provides guidelines for box fill calculations to ensure that boxes are not overcrowded, which can lead to overheating and other hazards. Fifthly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. The size of the overcurrent protection device must be matched to the ampacity of the circuit conductors. Sixthly, GFCI and FCI protection. Ground fault circuit interrupters, GFCIs, and arc fault circuit interrupters, FCIs, are special types of circuit breakers that provide additional protection against electrical shock and fire hazards. GFCIs are typically required in wet locations, such as bathrooms and kitchens, while FCIs are required in bedrooms and other areas where arc faults are more likely to occur. Seventhly, voltage drop calculations. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Voltage drop calculations should be performed to ensure that the voltage at the load is within acceptable limits. Eighthly, electrical symbols and diagrams. The electrical symbols and diagrams are used to represent electrical components and circuits in a standardized way. Understanding electrical symbols and diagrams is essential for troubleshooting and maintaining electrical systems. Ninthly, electrical testing and troubleshooting. Electrical testing and troubleshooting involve using various instruments, such as multimeters, voltage testers, and clamp-on ammeters to diagnose electrical problems. Common electrical problems include open circuits, short circuits, ground faults, and voltage drops. Tenthly, energy efficiency and conservation. Energy-efficient lighting, appliances, and wiring practices can help reduce energy consumption and lower utility bills. Energy-efficient electrical systems also reduce the strain on the electrical grid and help conserve natural resources. The following expands upon specific aspects of electrical wiring and safety, providing further context and guidance. Firstly, understanding the neutral conductor. The neutral conductor in an electrical circuit carries the return current from the load back to the source. In a properly wired circuit, the neutral conductor should be at or near 0 volts relative to ground. Secondly, importance of proper connections. Making proper electrical connections is crucial for safety and reliability. Loose or corroded connections can cause overheating, voltage drops, and even fires. All electrical connections should be clean, tight, and properly insulated. Thirdly, working with aluminum wire. Aluminum wire is commonly used in older electrical systems, but it requires special handling to prevent corrosion and overheating. Aluminum wire should be properly terminated with connectors and antioxidant compounds approved for use with aluminum. Fourthly, using wire connectors. Wire connectors, such as wire nuts and terminal blocks, are used to join electrical wires together. It's important to use the correct type and size of wire connector for the wires being joined. Fifthly, identifying circuit breakers. Circuit breakers are used to protect electrical circuits from overloads and short circuits. Each circuit breaker should be labeled to indicate the circuit it protects. Sixthly, working with Romex cable. Romex cable is a type of non-metallic sheath cable commonly used for residential wiring. Romex cable should be properly supported and protected from physical damage. Seventhly, using junction boxes. Junction boxes are used to enclose electrical connections and provide access for future maintenance. All electrical connections should be made inside junction boxes. Eighthly, bonding metal enclosures. Metal enclosures, such as electrical panels and junction boxes, should be bonded to ground to provide a path for fault current. Bonding helps prevent electrical shock hazards. Ninthly, testing for voltage. Before working on any electrical circuit, it's important to test for voltage to ensure that the circuit is de-energized. A voltage tester should be used to verify that the circuit is safe to work on. Tenthly, importance of ongoing maintenance. Regular maintenance is essential for ensuring the safety and reliability of electrical systems. Electrical systems should be inspected periodically for loose connections, damaged wiring, and other potential problems. When working with electrical wiring and circuits, always prioritize safety and follow established electrical codes and practices. When dealing with electrical systems, it is imperative to have a comprehensive understanding of various codes, regulations, and best practices. Below is a more in-depth exploration of key aspects related to electrical safety and compliance. Firstly, NEC Article 210 branch circuits. Article 210 of the National Electrical Code, NEC, provides requirements for branch circuits, including conductor sizing, overcurrent protection, and receptacle placement. Understanding and adhering to Article 210 is essential for designing and installing safe and code-compliant branch circuits. Secondly, NEC Article 250 grounding and bonding. Article 250 of the NEC covers grounding and bonding requirements for electrical systems. Proper grounding and bonding are crucial for minimizing the risk of electrical shock and ensuring the safe operation of electrical equipment. Thirdly, NEC Article 300 wiring methods. Article 300 of the NEC addresses wiring methods, including requirements for raceways, cables, and conductors. Compliance with Article 300 is essential for ensuring that electrical wiring is installed safely and in accordance with industry standards. Fourthly, NEC Article 310 conductors for general wiring. Article 310 of the NEC provides guidelines for selecting conductors for general wiring, including ampacity ratings and dating factors. Properly sizing conductors is essential for preventing overheating and ensuring the safe and reliable operation of electrical circuits. Fifthly, NEC Article 400 flexible cords and cables. Article 400 of the NEC covers flexible cords and cables, including requirements for their use, construction, and ampacity. Understanding Article 400 is essential for selecting and using flexible cords and cables safely and in accordance with code requirements. Sixthly, understanding lockout-tagout procedures. Lockout-tagout procedures are essential for preventing accidental energization of electrical equipment during maintenance or repair. These procedures involve energizing the equipment, locking out the power source, and tagging it to indicate that it should not be re-energized. Seventhly, using personal protective equipment. Personal protective equipment, PPE, such as insulated gloves, safety glasses, and arc flash suits, is essential for protecting workers from electrical hazards. PPE should be selected based on the specific hazards present in the work environment. Eighthly, understanding arc flash hazards. Arc flash is a dangerous electrical phenomenon that can occur when a short circuit or other fault causes an electrical arc. Arc flash can produce intense heat, pressure, and light, resulting in serious injuries or fatalities. Ninthly, performing electrical safety audits. Electrical safety audits are conducted to identify potential hazards and assess compliance with electrical safety standards. These audits can help organizations improve their electrical safety programs and reduce the risk of accidents. Tenthly, providing electrical safety training. Electrical safety training is essential for ensuring that workers have the knowledge and skills necessary to work safely around electricity. Training should cover topics such as electrical hazards, lockout-tagout procedures, and the proper use of personal protective equipment. By adhering to these codes, regulations, and best practices, organizations can create a safe and compliant electrical work environment. When working with electrical systems, it is essential to consider a range of practical aspects that can influence the safety, efficiency, and reliability of the installation. Here are some important practical considerations to keep in mind. Firstly, planning the layout of electrical circuits. Before starting any electrical work, it is important to plan the layout of the circuits carefully. Consider the location of outlets, switches, and lighting fixtures, and ensure that the wiring is routed in a way that minimizes interference and maximizes safety. Secondly, choosing the right type of wiring. There are several types of electrical wiring available, each with its own advantages and disadvantages. Choose the type of wiring that is best suited for the application, considering factors such as ampacity, voltage rating, and environmental conditions. Thirdly, selecting the appropriate size of conduit. Conduit is used to protect electrical wiring from physical damage and environmental factors. Choose the appropriate size of conduit based on the number and size of wires that will be installed inside it. Fourthly, installing grounding and bonding systems. Grounding and bonding systems are essential for ensuring electrical safety. Install these systems in accordance with the NEC and local codes, and verify their effectiveness through testing. Fifthly, properly terminating electrical connections. Properly terminating electrical connections is crucial for ensuring reliable performance and preventing electrical hazards. Use the correct type of connectors and tools, and follow the manufacturer's instructions carefully. Sixthly, labeling electrical panels and circuits. Label electrical panels and circuits clearly and accurately. This will make it easier to identify and troubleshoot problems in the future. Seventhly, testing electrical circuits. Before energizing any electrical circuit, test it thoroughly to ensure that it is wired correctly and that there are no shorts or ground faults. Eighthly, protecting electrical equipment from moisture. Moisture can cause corrosion and electrical hazards. Protect electrical equipment from moisture by using weatherproof enclosures and sealing connections. Ninthly, providing adequate ventilation for electrical equipment. Electrical equipment generates heat, which can cause it to overheat and fail. Provide adequate ventilation to prevent overheating and ensure reliable performance. Tenthly, performing regular maintenance on electrical systems. Regular maintenance is essential for ensuring the safety and reliability of electrical systems. Inspect wiring, connections, and equipment regularly and repair any problems promptly. By considering these practical aspects, you can ensure that electrical installations are safe, efficient, and reliable. When working with electrical systems, it is crucial to understand and apply various testing and troubleshooting techniques to ensure safety and identify potential issues. Below are essential testing and troubleshooting techniques for electrical systems. Firstly, voltage testing. Voltage testing is used to verify the presence or absence of voltage in an electrical circuit. Use a voltmeter or voltage tester to check for voltage at various points in the circuit, such as outlets, switches, and terminals. Secondly, continuity testing. Continuity testing is used to verify the integrity of electrical conductors and connections. Use a multimeter set to the continuity setting to check for continuity between 2 points in the circuit. Thirdly, insulation resistance testing. Insulation resistance testing, also known as megometer testing or mega testing, is used to assess the condition of insulation in electrical wiring and equipment. Use a megometer to measure the insulation resistance between conductors and ground. Fourthly, ground resistance testing. Ground resistance testing is used to measure the resistance of the grounding system. Use a ground resistance tester to verify that the grounding system is effective in providing a low impedance path for fault current. Fifthly, circuit breaker testing. Circuit breaker testing is used to verify the proper operation of circuit breakers. Use a circuit breaker tester to check the tripping characteristics of circuit breakers and ensure that they are functioning correctly. Sixthly, GFCI testing. GFCI testing is used to verify the proper operation of ground fault circuit interrupters, GFCIs. Use a GFCI tester to simulate the ground fault and verify that the GFCI trips as designed. Seventhly, power quality analysis. Power quality analysis is used to assess the quality of electrical power, including voltage, current, frequency, and harmonics. Use a power quality analyzer to identify and address power quality problems that can affect the performance and reliability of electrical equipment. Eighthly, thermal imaging. Thermal imaging is used to detect temperature differences in electrical equipment and wiring. Use of thermal imaging camera to identify hotspots that may indicate loose connections, overloaded circuits, or other problems. Ninthly, troubleshooting open circuits. An open circuit is a break in the electrical path that prevents current from flowing. Use a multimeter to check for voltage and continuity to locate the open circuit. Tenthly, troubleshooting short circuits. A short circuit is an unintended electrical connection between two conductors that causes excessive current to flow. Use a multimeter to check for resistance and voltage to locate the short circuit. By using these testing and troubleshooting techniques, you can ensure the safety and reliability of electrical systems and identify potential problems before they cause damage or injury.